Greetings, everybody. So in this video, we're going to give you an introduction to the topic of chaotic encryption. I have a lot of videos in my channel discussing about chaos and about various aspects of encryption. So I want to make a much more general video talking about chaotic encryption. Okay. So I'm going to talk a little bit about chaos. Of course, I have many videos in my channel about chaos. And then I'm going to discuss the three aspects that have to do with encryption, which is chaotification, PRBGs, pseudo-random bit and number generators, encryption itself, of course, and then discuss some future challenges in the field. So let's begin with the basics. Chaos. Now, in physics and mathematics, of course, I have many videos in my channel about chaos. In physics and mathematics, chaos refers to systems that are either described in continuous time through differential equations or in discrete time through difference equations, and these systems have nonlinear functions describing their relations and show an extreme sensitivity to initial conditions. What does this mean? This means that solutions that start from almost identical conditions, but very slightly different, over time will give rise to completely different solution trajectories. I have an example right here. I have a system in discrete time, a very famous system, the logistic map. And I plot, I think, around 50 different solutions. All of them start from very close to zero point 0.1, a very minuscule change in between them. And you see that over time, initially for the first few iterations, the solutions look exactly the same. So this difference between them remains small. But after a few iterations, this small difference in the initial conditions becomes larger and larger and larger. And then eventually, the trajectories completely diverge with each other and become completely different. Okay, so this is an example of the so-called butterfly effect. Chaotic systems have this very specific characteristic in their behavior. And chaotic systems are actually all around us. I would dare say you will not find a linear system in nature. Most of the systems that appear in nature, in physics, in engineering, in biology, in chemistry, economics, whatever, all of them have a chaotic nature in them. Okay, I doubt you will find a linear system in the real life. Okay. So a very big part of chaos and chaos theory is to model phenomena in nature. But since it's very relatively easy to generate a chaotic trajectory in a computer simulation, chaotic systems are a very nice low source of high unpredictability. So they also use them as tools for data encryption, watermarking, secure communications, path planning, and in general, I would say applications related to security. And that's our topic today. Okay, one of these applications is chaotic encryption. So what do we have in chaotic encryption? The design is very simple. We have some information that we want to encrypt. This can be image, text, or sound. And we are using a chaotic system to generate a chaotic solution. Okay, so this solution, which is basically time series, is then used, okay, through a collection of specific rules or an algorithm, if you like, to encrypt this sort of information that we want to transmit safely. So we encrypt through an algorithm using a chaotic system some sort of information, which is then safe to transmit because it's uncipherable. It doesn't provide any information. And then what happens? At the receiver end, the receiver will use the exact same chaotic system with the exact same initial condition and parameters, which are called the keys of the system. They will generate the exact same solution and then reverse the encryption algorithm to obtain the information back. So this is the whole process in chaotic encryption, and this is called symmetric encryption. There are several aspects now that have to do with the state of the art in the analysis of chaotic encryption at the moment. One of them is the design of suitable chaotic maps, another is the design of efficient bit generators, and the other is the design of efficient algorithms. These are three aspects of chaotic encryption that are being studied at the moment. So let's talk about the first part, the topic of heavy suitable maps. What does this mean? Well, the point is that, in the literature at the moment, there are many chaotic systems, but we cannot use them all in encryption. Not all of them are suitable. And the reason for this is that basically, if you consider any chaotic system, it has some parameters. It will not give chaotic behavior for all parameter values. So here, for example, I have the logistic map, and basically the logistic map for some values of the parameter, it is chaotic, as you see down below. But for other parameter values, it is periodic. So when it is periodic, it is not suitable for using encryption. Okay. And this behavior happens for many systems. It's not just the logistic map. Okay. So this, for example, bifurcation diagram. All of these lines that you see here correspond to periodic behaviors. Okay. The dense regions right here correspond to chaos. The problem is that this system goes in and out of chaos constantly. So I cannot use it because when I want to set the parameters for the design, I will not be entirely sure if my parameters that I choose will give me chaos or not. Ideally, I want systems that give chaos through and through. So all of the other dynamical phenomena related to chaos, like periodicity, crisis, and whatever, these are undesirable in chaotic encryption. Okay. So first thing is this: we need systems that have only chaos and nothing else. And other aspects of this design is the fact that we need very fast systems because encryption needs to be fast. And we also need secure systems. We need systems that cannot be breakable by simple algorithms. Okay. So all of these aspects let us know that not all chaotic systems are suitable for use. And this brings us to the topic that aims to resolve this issue, which is chaotification. Okay. So what is chaotification? As I told you in the literature, there are many chaotic systems that exist. Okay. So, since there are not all of them suitable for using chaotic encryption, what we want to do is design new systems with specific desirable characteristics. But the idea is this, instead of designing one specific system, what I want to do is ideally create a collection of systems, or I should say an algorithm or a technique where we can input any existing system and as an output obtain a new system that has a collection of desirable characteristics like chaos everywhere, okay, a very highly Lyapunov exponent, maybe no equilibria, maybe be lightweight, several characteristics that are desirable for encryption. So this is called chaotification. It's the process of taking any existing system and designing new systems that have better behavior than before. Okay, let me give you an example. Above we have the bifurcation diagram for the sign map, which is a very well-known map. And the sign map showcases periodic regions. So here this region is periodic, 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 some periodic windows right here. So the sign map goes in and out of chaos constantly, goes chaos period, chaos period, chaos period. After chaotification, we have the diagram that you see below, where you don't see any periodicity. So the chaotified map is a new map that has chaos everywhere. Okay. So this is what we aim to do with chaotification. We want to have new maps with chaos everywhere, and ideally, of course, not being heavy in computational time. We also need to have them be lightweight. This is another example of amazing chaotification. See, for example, on the left, you see a diagram that shows the Lyapunov exponent for a system as we change two parameter values, A and B. So the color here represents the Lyapunov exponent and black represents periodicity. So on this system, you see that as we change the parameters, we go between chaos, order, chaos, order, chaos, order. So we constantly go between black regions and colored regions. This is undesirable. On the other hand, you see the right graph, you see another system, and you see here that as we change the parameters A and B, the Lyapunov exponent, as you see in the color bar right here, is always positive. So in a very big parametric range, we have only chaos, nothing else, no periodicity at all. Okay, so this is an amazing, desirable result in chaotification. So that's the goal of chaotification, achieve something like that, ideally at a low computational cost. So this is a very big topic in mathematics and physics and in encryption as well, but it is also irrelevant to encryption. It's a very big mathematical problem. The design here consists of geometric analysis, mathematical analysis through the Lyapunov exponents, key space analysis to show how big are the possible solutions that we get, the possibly different solutions that we can get, speed, so how lightweight is the chaotification, and of course this is the mathematical part, but we also have a numerical part where we plot many different diagrams to study the behavior of any design system. Okay. So this is the very big first problem in encryption, designing good chaotic maps. The second big topic is chaotic random bit generators. Okay. PRBGs or random bit generators are basically a function that generates random bits, okay, or random numbers. And PRBGs are especially useful because if you want to design an encryption algorithm, you need to have a collection of random numbers to use in your algorithm. Okay. So basically, PRBGs are the essential part of a chaotic encryption algorithm. How do they work? Okay, they work like this. We have a chaotic system at hand. So first we set the parameters of the chaotic system, initial conditions and parameter values. These are the keys of the system. Okay. And then we simulate the chaotic system. We obtain a solution from this chaotic system. And then this solution, which is basically a time series, is passed through a function. This is called the hash function. And the function, through some algorithm, through some methodology, outputs in each iteration a collection of random bits or random numbers, depending on what we like. So there are several topics here that need to be designed to have a good PRBG. We need to have a very big key space. This is basically the number of different solutions that we can get. So we need to have a system with many parameters. This makes sure that we're resistant to brute force attacks. The chaotic system and the hash function, of course, need to be lightweight. So we cannot have a generator that takes far too long to generate the bits. It needs to be fast. Okay, this is very important. And additionally, the hash function should be a nonlinear function that hides the relation between the chaotic system and the output. So it needs to be secure against estimation attacks, or which are called, in the literature, cryptanalysis attacks. We need to have a function that hides the chaotic system from the output bits. Because this way, if I have an outsider that takes a look at the bits, he will not be able to guide or to get any information about my chaotic system. This is very important from a security perspective. Okay, so we need to have a good hash function. After all of this, of course, are satisfied, the output bits need to be just like random noise. Okay, so we need to have very extreme statistical randomness, because if the output bits are not statistically random, the encryption will fail. Okay, that's the whole point of having pseudo-random bit generators. So let me give you an example of a bad PRPG. So here I have the solution of a logistic map, okay, a very basic chaotic system. What you see here is the black line. And my hash generator works like this. If the time series is above 0.5, the output of the generator is a 1. If the time series is below 0.5, the output generator is a 0. Okay, so this is a very, very basic threshold comparison. So the time series gives 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, and so on. Okay, so this is a good generator. Well, it is extremely fast, which is a good thing, but the generator is very bad. Why is it bad? Because it is not secure enough. It gives out far too many information about the underlying time series. Because when I look at the output bits, I get immediately information about the values of the map. So this is not very good because I can design an algorithm that can easily break this generator and estimate the values of the map. Okay, so this is a fast PRBG, but it is not a safe PRBG. Okay, so this is an example of what we should avoid doing in the literature. Now, the whole analysis for generating very good PRBGs has to do basically with taking advantage of the time series and the least significant digits. So in the decimal representation, we usually use the least significant digits to design good PRBGs. I'm not going to give you any details now, doesn't matter. I have other videos explaining. Okay, after we design PRBGs, it is important to do a formal analysis on the brute force sensitivity and the brute force attack on this generator. So we have to analyze specifically what information does the generator give on the chaotic map and if we are secure enough against attacks. And then, of course, it is very important to have a very speedy PRBG because encryption needs to be fast. So now that we have designed ideally good chaotic maps and good PRBGs, we can move on to encryption. So in encryption here, we are going to use good chaotic maps and good PRBGs. As I told you, the idea is that we are having a nice map, we are generating a PRBG or a PRNG, a number generator, and through an algorithm, we are encrypting some data, transmitting them, and of course the algorithm should be reversible because the receiver needs to obtain the information back by reversing the encryption process. So in encryption and chaotic encryption and encryption in general, there are two basic aspects of hiding data. One is shuffling. Consider a deck of cards where we shuffle the deck of cards so that we disperse information and we don't know the order that the information of the deck of cards is now. Okay, so shuffling is very important to disperse information in the text, in the plain text. So for example, here in an image, consider shuffling the pixels of the image. Okay. And the second action is substitution. In this action, we take each part of the information, a pixel for example, and substitute it with another value. Both of these actions are important. You cannot have just one of them. In order to have secure encryption, you need to have both actions being performed. Okay? So we perform them using chaotic rules, not chaotic rules, sorry, let me correct this, using an algorithm that uses chaotic random numbers or random bits that we have from our generator. How do we do though? We can use it either in the algorithm pretty much works the same way if we use it on text data, sound data, video data, or image data. Image data are more common because they have structural design, okay? So, an image, remember, is basically a matrix. And I'm saying this because in many encryption algorithms, just as a side note, we use a lot of linear algebra techniques. It's pretty standard because by linear algebra, we can basically process matrices very, very easily. Okay, so just as a side note, you may need to know some linear algebra to do image encryption, which is not necessary, of course, just some techniques use it. So, in order to have a good encryption algorithm, what should we do? We should basically motivate each step, okay, explain why we are performing each step. And with this way, we can avoid redundant steps because many papers at the moment in the literature perform many steps that are not required. So we need to explain why we are doing each step and avoid redundant steps. After we do that, we can have an algorithm that is ideally fast, ideally resistant to cryptanalysis. And of course, we can do that through a theoretical analysis and also through a numerical analysis. Okay. By the way, there are some other approaches at the moment in the literature that consider other techniques that are usually in the frequency domain, but I'm not going to analyze them. There are relatively, I would say, newer in the literature. So, the shuffling and the substitution can happen usually when we are considering images in the pixel level. Remember, an image is a matrix, as I told you. Each element in the image is basically a pixel. So we're shuffling pixels, we're substituting pixels. Another technique is a bit more analytical and more secure is to use the binary representation of the image. So we take each pixel, represent it as a bit, and then perform shuffling and substitution on the bits. So what you see on the right here are actually the bit representation of the image. Each byte has 8 bits, so we basically have 8 bits per pixel. Okay, so this is the binary representation of the image. And shuffling substitution can be performed in either binary level or bit level. So let me give you a very short example of an encryption algorithm. Here I have the existing original image that I want to read. I break the binary information and I arrange the binary information in a very, very large rectangular matrix. And then how do I do the shuffling? I shuffle each of these rows in the matrix. So we perform row shifting. So basically, we change the relative order of the bits in the rows. Then on the next step, we perform shifting on each individual column. So we again change the relative position in the columns. So we've performed these two steps, which basically change the relative position for all of the bits in the image. This is basically a shuffling process. Okay, we disperse the information and shuffle the information around the image. After we do that, we can obtain the original gray image back by arranging the bits together. Okay, and then the substitution process is usually performed through an operation that is called exclusive OR. I'm not going to give you the details of exclusive OR. What you need to know is just that exclusive OR is, an operation that is reversible. So we can reverse it back, which is of course important because we need to decrypt the image as well. So in order to perform substitution, we perform this XOR or exclusive OR operation between the shuffled image and an image that results from a random number generator. So we generate basically random pixels and then combine them together for substitution. And the result looks something like that. This is the original image, this is the shuffled image, and this is the completely encrypted image. After both of these steps are performed, substitution and shuffling. Okay. The encrypted image, as you see here, looks basically like random image noise. Okay. Which means that if an outsider looks at this image, they cannot obtain any information about the aeroplane image that I have on the left. Okay, so that's how encryption should work. Now, after we have performed our encryption algorithm, there is a collection of tests that are very standardized in order to evaluate how good the encryption is. Okay, let me give you just some very few examples on that. One classic analysis that we do on an image is compute its histogram. The histogram of an image gives us basically the distribution of the pixel values. So here, for example, any random image that we have, not random, sorry, any non-random image will have a non-uniform histogram because it depicts information. But after encryption, the histogram of the image is completely uniform. This tells us that the distribution between different shades of gray is completely uniform. We cannot obtain any information by looking at this encrypted image, which is a good result. The same holds for the correlation between pixels. So, in an actual image, pixels that are very close to one another have very close values. That's why you see this uneven distribution between relatively close pixels in an image. After encryption, images that have pixels, the pixels in the image that are very close to each other should have values completely irrelevant. Can we achieve that? We should be able to achieve that. If we don't achieve that, we don't have a good encryption. Here we actually do. Another very good result that we can achieve by performing both substitution and shuffling is resistance to information loss. So here, for example, see this. In an original image where I don't perform the shuffling during encryption, if some sort of information is lost, let's say here the top left, then during the decryption, the same part will also be lost. So here on the top left, let's say we somehow lost it during transmission, well, we cannot retrieve it back. But if we perform shuffling during the encryption, the same part that is lost here can be actually retrieved through the decryption process. But the downside is that this lost information is dispersed throughout the original image. Basically, this is a good thing because it tells us that if we lose spatial information in the image, we can actually manage to retrieve the spatial information back, okay? Because this loss is actually dispersed throughout the image itself. So basically, through this dispersion, we can retrieve all parts of information from the image, which is a very good result. In order to achieve this, you need to have shuffling during the encryption process. Okay. So we have information loss in a good encryption. Okay. And of course, the information loss can go up to very high levels. See here, for example, 75% of the image is lost, but still we have managed to get some sort of information back. Okay. We also have resistance to noise, so any type of noise can help us retrieve some information from the image. And ideally, all of the above should be able to work at a very low execution speed. So ideally, the encryption should be very, very low, much less than a second for a big image. So even for very, very big images, 1024 by 1024, the speed should be 0.2 and even lower in order to encrypt. Of course, we are talking about very big data here, but ideally encryption should be very, very, very fast. Okay. So that's the basics about encryption. Now, let me talk about the future challenges. I'm going to give you some examples of what are topics that are very relevant at the moment. You can have thesis reports, PhD, master thesis, papers published out of these topics. They are very, very interesting and very state of the art. So one of these topics, oops, I'm sorry, is lightweight chaotification. So this is a topic, of course, that it is basically a mathematical problem and a problem in physics, but it also very relevant to encryption. Okay, so codification of systems with good results at a very low execution cost is a very nice mathematical problem. I strongly suggest you take a look at it. I'm very active at this moment, at this problem at the moment. It's a very interesting topic and, of course, very relevant to chaotic encryption. There are many, many works to be done at this problem at the moment because we are constantly trying to improve our techniques. Okay, so one topic is chaotic lightweight chaotification. Lightweight chaotification. Another big problem in cryptanalysis is provable security. So it's very hard to formalize the analysis of chaotic security, and so theoretically that we have an absolutely secure encryption design. This is a very big problem. very state of the art at the moment, and I believe it requires a formalization for the protocols for chaotic analysis on encryption. Very, very interesting topic. And another problem, of course, I don't do research in this, but it is very, very state of the art, is the reproducibility and implementation of chaotic systems in different devices. So in different languages, Python, MATLAB, in Arduino, in microcontrollers, in FPGA, in smartphones, in Internet of Things devices, implementation of chaos encryption across devices is a very interesting and very active topic at the moment. Again, very state of the art. Another very big problem, very state of the art, I believe you can have many different works published on this topic, is the use of chaotic encryption along deep learning. So at the moment, there are a couple of papers that try to combine deep learning with chaos encryption. I believe it's going to be very highly state of the art as a topic and many improvements to be done over the next few years. So a very interesting topic of study. Another very interesting topic of study is the use of chaotic encryption in order to encrypt neural networks. For example, to protect intellectual property, you can design very fast encryption techniques for encrypting weights in a neural network in order to make the design of the neural network secure against intruders. This is a very interesting topic of study. You can take a look at this paper right here. And another topic is the cryptanalysis of chaotic encryption through deep learning. Okay, so designing deep learning algorithms and architectures in order to be able to attack and unmask chaotic encryption. There are a couple of papers published. I believe it's going to be a very interesting topic for the future. Okay, so overall, okay, thank you very much for watching this video. I believe there are many topics in chaotic encryption that at the moment and in the near future for many years are going to be very interesting topic of studies. Of course, these are not the only ones. There are other topics as well. If you have any questions, write them down below. I'm sorry. Many papers that you can read on the topic. It's a very state-of-the-art topic with many aspects that are up to improvement. Okay, so happy reading. There are many papers to read. Focus on the best ones and the more recent ones. Constantly, we have new results on chaotic encryption. I hope you like reading it. You can watch other videos on my channel that have to do with chaotic encryption. And of course, you're gonna learn a lot of stuff if you watch